Hello everyone, how's it going? My name is Dan the Tutor. Today we're going to be talking about my favorite test from series in Calc 2, and that is the ratio test. Why is it my favorite? I don't know, I just enjoy it the most, so it's my favorite. So first I'll give you the equation for the ratio test. If you have some series a sub n, like you put in anything you want for a sub n, like for instance 1 over n factorial, whatever you want to put there, then all you need to do is you say the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, and you are going to evaluate this limit, and you're going to get one of three results. The first result you get is greater than 1. If you get an answer greater than 1, it's going to diverge your series. If you get less than 1, then your series will converge. And if you equal 1, then we would say the test was inconclusive and we would have to use another test. Now I'm going to show you how to do all of this, so let's go ahead and just jump into an example problem. Let's say I have the series from n equals 1 to infinity of 3 to the nth power divided by n factorial. So this is a great time to use the ratio test. And the reason why is because the ratio test works great for two scenarios. The ratio test works great for factorials, which is the exclamation point, and two, it works great when n is in the exponent. Now in this example, we have both of those. We have n factorial and an n in the exponent. So the ratio test is going to work great for us. So the first thing I need to do is, if this is my a sub n, 3 to the n over n factorial, I now need to find my a to the n plus 1. So here's what I'm going to do. I'm going to say wherever I have n, like here and here, I'm going to replace it with n plus 1, and it's going to look like this. 3 to the power of n plus 1 divided by, in parentheses, n plus 1 factorial. That's all you do. It's not too bad. I just replaced my n's with n plus 1. That's what you do for the ratio test. Now what we're going to do is we are going to divide these two things. Limit as n goes to infinity. I know there's supposed to be absolute value, but there's nothing negative here, so I'm just going to ignore that for right now. 3 to the n plus 1 over quantity n plus 1 factorial. That's my a sub n plus 1. And then divided by a sub n, the original, which is 3 to the n over n factorial. So now, this is complicated. It's also known as a complex fraction. So what I'm going to do is I'm going to invert the second and multiply. It's going to look like this. Limit as n goes to infinity of 3 to the n plus 1 over n plus 1 factorial times n factorial over 3 to the n. See how I flipped the denominator and multiplied? That's how we deal with complex fractions. And now this is a lot nicer. It may not look nicer because you might not know how to evaluate this limit, but I'm going to tell you this is great actually. And so first, I want to explain the 3 to the n plus 1 because this is the easier thing to explain. 3 to the n plus 1 is actually just equal to 3 to the n times 3 to the first. I'm not sure if you knew that, but this is true, so I'm going to replace it with that. I'm going to say 3 to the n times 3 to the first, and then I want to replace the n plus 1 factorial as well. So many of you out there probably don't even know what factorials are, so let's start by explaining that just real quick. If I have 5 factorial, that's the same thing as 5 times 4 times 3 times 2 times 1. Basically, a factorial is just saying multiply by one less number until you get down to 1. So when I have n factorial, I would say that that's equal to n times n minus 1, because that's the next term, and then times n minus 2, and then n minus 3, and then you get the picture. Now, I don't have n factorial, or if I do, I don't really care. I have n plus 1 factorial, which would be written out as n plus 1 times just n times n minus 1 times n minus 2. Again, you get the picture. Now, these two things are almost identical to each other. See how n factorial is almost the same thing as n plus 1 factorial? As a matter of fact, if I circle this part and this part, I would argue that those parts are the same, and they are. So basically what I'm trying to say is, if you want to simplify n plus 1 factorial, then you would just write quantity n plus 1 times n factorial. It may not make perfect sense to you right now, but I promise you, when you see n plus 1 factorial in Calc 2, you want to rewrite it like this, n plus 1 times n factorial. So now let me plug it back in to what I was saying earlier. We had 3 to the n times 3 to the first. Divided by n plus 1 factorial, we just simplified to n plus 1 times n factorial. And then we are still multiplying by n factorial over 3 to the n. Now the reason why this strategy works so well is because now the n factorials will cancel. The 3 to the n's will also cancel. And it looks like you're just left with the limit as n goes to infinity of 3 to the first, which is just 3, divided by n plus 1. And if you know your limits at infinity, you know this is going to be 0. Now I don't care that it equals 0 as much as I care that that number is less than 1, and by the ratio test we would say that converges. So this series is going to converge. And the cool thing about the ratio test is that if you were to use any other test to try and prove that this series converges or diverges, I'll tell you that just about every test out there wouldn't work except the ratio test and the direct comparison test. And I don't like the direct comparison test because it takes me a while and I have to think about it. But the ratio test is really quick, especially when you know what you're doing. And again, it works great for whenever you have factorials or an n in the exponent. It's actually kind of funny. The ratio test is a really smart test, but it can't even be used to prove 1 over n, the harmonic series, which we all know diverges. The ratio test is not smart enough to figure that out, that it diverges. And the reason why is because if you have like 1 over n plus 1, which is the n plus 1th term, the limit as n goes to infinity, 1 over n plus 1 over 1 over n, again, reciprocal and multiply, limit as n goes to infinity of now 1 over n plus 1 times n over 1, which can just be written as n over n plus 1. As you can see here, this limit is just going to be 1, which we would say is inconclusive. So in other words, the ratio test is great, but not every time, only for n factorial or an n in the exponent. So now let's look at the next one. I have the series from n equals 1 to infinity of, let's say, 5 to the n over quantity n plus 1 squared. So again, I have an n in the exponent here. I can use the ratio test, and I like the ratio test, so I'm going to use it. The first thing I need to do is, if that's a sub n, I need to find a sub n plus 1. I just add 1 wherever I see n, so the numerator is easy, 5 to the n plus 1. For the denominator, it's like I have n plus 1 plus 1, because there's already a plus 1 there, so you do n plus 1 twice. If you want to, you can write n plus 2 squared, and I am going to do that because I think it's easier. And so now I am just going to do the limit as n goes to infinity of a sub n plus 1, which is the 5 to the n plus 1 over n plus 2 quantity squared. And instead of dividing by the complex fraction, I'm smart enough to know that I'm just going to multiply by the reciprocal anyway. So the reciprocal would be n plus 1 squared in the numerator now. And in the denominator now is 5 to the n. So now let's talk about simplifying this. For the numerator, 5 to the n plus 1, we're going to do the same trick we did before. It's 5 to the n times 5 to the first. Easy peasy. In the denominator, n plus 2 squared. I don't actually have to FOIL that, but I will for you because I like you so much. N plus 2 squared is n squared plus 4n plus 4. And then that is times n plus 1 squared, again I'll FOIL that out, n squared plus 2n plus 1 divided by 5 to the n. There's only one thing that cancels here, and it's the 5 to the n. Nothing cancels here and here because of all the plus signs really mess us up, and that's fine, they don't have to cancel. But now what I have is the limit as n goes to infinity of 5 times n squared plus 2n plus 1 divided by n squared plus 4n plus 4. Now, if you think of your limits at infinity rules, I would say that the degree of the numerator is the same as the degree of the denominator. They're both n squared. So you look at the coefficients out in front. The coefficient of the numerator is this 5, and the coefficient of the denominator is just 1. So the answer is going to be just 5 over 1. Now 5, which is what that is, it's 5, is greater than 1, so we instantly know it diverges by the ratio test. Now one more thing I do want to say for this problem is that earlier I mentioned the fact that you didn't actually have to FOIL out the n plus 1 and n plus 2 squared. And the reason for that is if you don't FOIL it out, you get this right here. And I would say for this one that I don't even need to FOIL it out. I know it's going to be n squared in the numerator and denominator, and my coefficient is still going to be 5 over 1. So you can get 5 without even needing to FOIL. Now if you're not confident, then yeah, I would definitely recommend FOILing, obviously. But you don't have to, is what I'm saying. And now for the last one we have today. It's the series from n equals 1 to infinity of n plus 2 factorial over 2n factorial, all in parentheses like that. So once again, the first thing I'm going to do is say that's a sub n, and then I'm going to find a sub n plus 1, and that's just going to be numerator n plus 1 will now be n plus 3 factorial. And you do have to be careful for the denominator, because the 2n like this, it's actually going to be parenthesis 2, second parenthesis, n plus 1, close parenthesis, factorial. Now that looks complicated, but basically in the denominator you just have 2n plus 2 when you distribute, factorial, and the numerator stays the same. So now, once again, I'm going to put the limit as n goes to infinity of a sub n plus 1, which is n plus 3 factorial over quantity 2n plus 2 factorial, and that is multiplied by the reciprocal of the original, because again, you can multiply by the reciprocal for complex fractions. And you're going to get 2n factorial over n plus 2 factorial, just like that. Once again, we need to start simplifying this. So the n plus 3, I'm just going to rewrite that as this. I'm going to write quantity n plus 3 times n plus 2 factorial. And this works because whenever you want to rewrite your factorials, you just subtract 1, and that's the next term. And the reason why I'm not going to keep going is because I see that that's now going to cancel with that n plus 2 factorial in the denominator. So I'm good for the numerator. The denominator is harder. So basically, if I have 2n plus 2 factorial, that's the same thing as 2n plus 2 times 2n plus 1 factorial, but I don't want 2n factorial because that's not going to cancel with the 2n factorial there. So I'm going to erase that factorial I just drew, and I'm going to keep going. The next term would be times 2n plus 0, which is just 2n factorial. Now I'm happy, because now it's going to cancel with the 2n factorial that I mentioned earlier. And then again times 2n factorial divided by n plus 2 factorial. Let's see what cancels. Looks like the n plus 2 factorial cancels with that one, and the 2n factorial cancels with that one. I am left with the limit as n goes to infinity of numerator n plus 3, denominator 2n plus 2 times 2n plus 1. You can FOIL that if you want to. However, I know the denominator is going to have the leading power of n squared, and the numerator is just n to the first. So due to my limits at infinity, degree of the denominator is higher. So I would say that this answer is definitely going to be 0, which means that's less than 1, and it converges. The series converges. Okay, so that's going to do it on today's lesson of the ratio test. I hope you had as much fun as I did. Thank you all for watching. I hope you have a great rest of your day. I'll see you in the next video. Take care, and bye-bye.